Alright, what's up guys? Today I'm going to be going over how to draw ray diagrams for mirrors. And in the next video I'll cover them for lenses, but today we're just going to focus on mirrors. Right, so what are the important things we need to know? I'm going to go over basic formulas, how to draw ray diagrams, and then how the formulas relate to the diagrams we draw, and how to figure out anything you need to know about mirrors. Right? So one of the most important things to understand is the ray model of light. Right? So this is the basis for how all light travels. Right? And it may, unless you figure out, if you have an image or an object, where the image is going to be in terms of a mirror. Right? So if I have a ball right here, right, and it's a pretty simple concept, the light that shines off the ball travels in rays, right, in pretty much straight lines. They are electromagnetic waves, but they travel in waves, and when those waves converge, right, when those light rays converge, that's when we see an image, right? So how does that relate, right? So first, you have to understand what I'm talking about in terms of mirrors, right? So there are two types of mirrors, concave and convex. Right, and they're essentially the same, right? Except concave, right? The center, the curvature is towards you, right? And convex, the curvature is away from you, right? So if there's a person right here, or an object right here, or an object right here, right? The curvature is towards this person, away from this person, right? Excuse me, right? So there's something in common, or something we can relate about these two mirrors, right? Is the amount of curvature they have, right? And the amount of curvature is measured by something we call R or C, right? Which is the center of curvature or the radius of curvature, right? So if I have an axis here, which is called the principal axis, that goes to the center of the mirror, right? Both mirrors, an eddy mirror, will have something known we call C, right? C. All C is saying, or R, center of curvature, or radius of curvature, is basically, if you were to extend this to be a full circle, right? And this is not really accurate, it's basically what would the radius of that circle be. Right? So if I were to extend this to be a full circle, the radius approximately would be here. Right? So that's what your center of curvature is. We have another point that's important, right? Well, it's R, that's F, right? And all F is equal to R divided by 2. So it's half the distance of your center of curvature. Okay, so how does this relate to drawing ray diagrams, right? So I'm going to go through all the possible scenarios of drawing image on a concave mirror. Right. So let's say I have a mirror like this. This is my principal axis. We have a mirror right here. Sorry, let me draw it again. We have F here, R here, right? So there's multiple scenarios which can happen, right? When we have an image and an object and image, right? And what I mean by those two words, right? An object is something you hold up to a mirror. So let's say I hold this marker up to a mirror, right? This is the object. The image will be either virtual or real, erect or upside down. It'll be magnified or smaller, right? And it'll either be it'll be a certain distance away from the mirror, right? So in a normal mirror, right, if you hold a marker up 3 meters away from the mirror, right, it'll be 3 meters deep into the mirror, right? So there's certain equations we have to map these different things we have, right? So those equations, first one is called the mirror equation. Right, which says 1 over dO plus 1 over di equals 1 over F. Right, and the other equation we have is the lateral magnification equation. Right, which states M equals HI over HO equals negative di over do. right? So what are these two equations? What do they mean? So the mirror equation first, DO stands from the distance the object is from the mirror, right? So if my marker is 10 meters away from the mirror, my DO will be 10 meters away. DI stands for the image, how far the image is from the mirror, right? So DI, if I hold the mirror up, or hold the marker up 10 meters away from the mirror, and the image shows to be 3 meters away, right? Then my DI, 3 meters away from the mirror, that is, DI would be 3 meters, right? If you have a negative DI, it means you have a virtual image, right? If you have a positive DI, it means you have a real image. What do I mean by virtual and real, right? So sometimes the light rays don't converge in real life, right? They converge behind the mirror, right? So if we have like a mirror, right? Behind the mirror is the image, or like the mirror's world almost, right? So if the light rays converge in the mirror's world, right, it'll be a virtual image. If it converges in real life, it'll be a real image, right? And then F, of course, is our focal point. Lateral magnification tells you how much the image has enlarged or shrunk, right? So if I have magnification greater than 1, right, so if my magnification is 2, it means if I hold up the marker to the mirror and the magnification is 2, it means in the mirror this will seem 2 times as large, right? Or if it's 0.5, right, it means if I hold up this marker to the mirror, it'll be half as large. HI is the height of the image, right? And HO is the height of the object, right? And that's also equal to negative DI over DO, right? So these equations will tell you, is the image real, virtual? Is it behind the mirror? Is it in front of the mirror? Is it larger? Is it smaller? Is it inverted, right? Is it upside down? So how do we use these equations, right, and map them in the real world, right? So if I don't have these equations, can I use ray diagrams, which I'll show you how to do, to figure out these properties of the image? So I'm going to go through the different options. So first, right, it's possible, right, that my object is right here, right? So if my object is right here, right, there's always 2 rays you want to draw to make an image, right? And the rule I like to remember is parallel F parallel. Right, so if you remember those rules, right, you should be able to figure out where the image is, right? So what I mean by that is you draw first a parallel line to the principal axis, right? So a parallel line to the principal axis from your object will always go through F, right? So this ray bounces back over the mirror and goes through F, right? Then F parallel, right, I draw another ray, goes through F, hits the mirror, bounces back. Where these light rays converge is where the image is, right? So these converge here, so my image will look like that, right? So what does this mean, right? So it means if the object is behind R, right, the image will always be inverted, right? Because you see this is inverted. It will be real, right? Because the light rays did converge, right? And the image distance will be between R and F, right? So this is always true, right? So let's do the next scenario. Right, so let's say I have my image here, my object here, right? Parallel F, parallel, right? And so I didn't draw this properly, but if I did draw it right with a ruler, right, you'll see, if you go parallel through F parallel, you'll see that your image distance, right, will be at your center of curvature. It will be at your radius of curvature. It will be the same size, so this technically should be the same size as this. I didn't draw it properly, but if I had drawn it right, this would be the same size as this. It would be a real image. It would be inverted, right? So this, you would get the same exact object except flipped over, right? So same size, it would be real, and it would be at the same point in space. So now, let's say I have it between R and F, right? So parallel F, right? F parallel might have not drawn this right, hold on. Parallel F, F, parallel. Yeah, so in the last diagram I had drawn the lines right, except in reality what you would see, every time the object is between R and F, right, you'll get an image that is a distance further away than the radius curvature. It'll be magnified because this is larger than this. It'll be inverted and it will be real, right? And I know the diagrams I'm drawing are a little shoddy, they're not 100% accurate, but the facts I'm telling you that they're magnified, inverted, real are true. But if you want to test it for yourself, feel free, you'll get this result every time if you have a ruler, right, and you have the correct distances for R and F for your given mirror, right? So the last two scenarios I'm going to draw are a little different than what we've been doing before. So let's say I have my F, my R, right, and now my object is at F, right? So, do my first ray diagram, right, parallel F, right, and I can't do F parallel anymore, right, because my object is at F, right, so my light rays won't go through F, right, so when this is the case, right, when you can't go through F, you will go through the center of the mirror, right, where the principal axis meets the mirror, right, and there's a special property about this, and when this happens, right, there's a certain rule that the light ray will bounce back at the same angle theta that it hits at, right? So it'll bounce back at the same theta, and you'll see, if you draw this properly, right, that these two rays will be parallel, right? These will never intersect, right? So that means that if you have an object at F, at the focal point of your distance, you will not have an image no matter what. And no matter how large it is and how small it is, right, you will never have an image produced if you have an object at F. Right, so the last one, let's say we have object less than F, right? We have F parallel, right? And then we have, go through the center, right? And we have a different angle of right here, right? So these angles will be the same, right? Because it hits right there, right? And these lines aren't parallel, but you see they're diverging, right? They're not gonna hit each other. I mean, in this area, right? So we have to look into the mirror, right? So when they don't converge here, right, we have to extend these rays back as if they went through the mirror, as if they originated from a point inside the mirror. And you get that they converge right here. So that means we have an image right here, right? So that image is magnified, it is erect, right? Still standing up straight. It's behind the mirror, right? Which means it's a virtual image, right? So if the actual light rays don't converge, we have a virtual image, right? These light rays, we can pretend as if they came from behind the mirror, right? And so that means we have a virtual image. We don't have a real image, we have a virtual image. But the rules are the same, right? Parallel F, right? We can't go through F, so we can't do F parallel. So we go to the center, to the principal axis where it intersects the mirror, and we draw a line that has the same angle as where it hit the mirror, right? So this angle and this angle are the same. Right, so that's all the possible scenarios for a concave mirror, right? We have beyond R, we have at R, we have between R and F, we have at F, we have between F and the mirror, right? So now let's look at convex mirror. So we have our principal axis, we have our convex mirror here, right? We have our F, we have our R, right? And we have an image anywhere on this side of the mirror. So remember, this is still behind the mirror, but our F and R on this side, this is in front of the mirror. So we have an object here, right? So we'll follow the same rules, parallel F, F parallel. So we go parallel, right? And we know this is a mirror, right? So the light ray will bounce back, right? So where does it bounce back? Parallel F, it'll bounce back as if the light ray was coming from F, right? Now we do F parallel, right? So we draw a line towards F, and how will it bounce back? It'll bounce back parallel, F parallel, right? Parallel to the principal axis, right? And we see that these two lines won't converge, right? So let me trace this one back, right? And we see that they converge, or they intersect here, right? So our image is here. So no matter where the image is, or sorry, no matter where the object is in front of a convex mirror, right? The image will be erect, it will be standing upright, it'll be smaller, diminished than the actual object, it'll be virtual, right? Because our light rays didn't actually intersect, right? And it'll always be between F and the mirror, right? So that is how to draw ray diagrams for any sort of mirror.